what I want to share. So we call it chemistry revision class, a revision class in chemistry. All right, so the first thing I want to share with you guys is reaction conditions. Right. We have several reactions that you need to know and their conditions before you go into the examination. All right, let's begin with some of the popular ones that we have. Of course, you know of the Haber process. All right, the Haber process, which is so Haber process is one of the reactions that you have in chemistry, IGCSE. So we have contact process, right? We also have the fermentation. Okay, we have fermentation. We have the process of esterification. Okay, so we have hydration. And then we also have hydrogenation. Right, and then we equally have the substitution reaction of the alkanes. Okay, so these are the major reactions that you have. Now, you must know the reaction conditions and equally the reactants or the reagents used in some of these processes. So if you've not done this, you're going to use this class to quickly revise it and, you know, prepare yourself to know them before going in. Because you'll be asked any of this, right? You can be asked any of this. So let's begin with the Haber process. The temperature is 450 degrees Celsius. Okay, the pressure is 20,000 kPa. Okay, and remember that if you are asked to present the kPa in ATM, all you need to do is to divide by 100. Okay, so it's either 20,000 kPa or it's 200 ATM. All right, and then for the catalyst, of course, you know it's iron. Iron is the catalyst in this process. So this is what you need to review for every process that you're looking for, you're going to work with. Now, for the contact process, and that contact process, we are simply talking about the production of sulfuric acid. Remember, this is for sulfuric acid, while the Haber process is for ammonia. Okay, the Haber process is for ammonia. Okay, so when we talk about the contact process, it has the same temperature as the Haber process. So it is still 450 degrees Celsius. But this time it is 2,000 kPa instead of 20,000 kPa like we said earlier. So it's 2,000 kPa. And if you divide, it's 200 kPa, sorry, not 2,000 kPa. It's 200 kPa, and then if you divide it by 100, you have 2 atm. Okay, so if you divide that by 100, you have 2 atm. All right, we say or 2 atm. Okay, and then the catalyst in this case is vanadium 5 oxide. Okay, vanadium 5 oxide. So these are the information you need to review as far as the reaction conditions are concerned. Then we also have the fermentation process. Now, what are the, of course, fermentation is the process by which, glucose is broken down, okay, to produce alcohol and carbon dioxide. All right, so what are the conditions that are needed for the process of fermentation? What you need is yeast, which is the enzyme there. And what you equally need for this reaction is it has to take place in the absence of oxygen. Okay, so absence of oxygen is equally important for the process of fermentation. All right, so these are reaction conditions for fermentation. Of course, you know that your reactant is glucose. Okay, I know what glucose is, C6H12O6. All right, the contact process, we are simply dealing with the sulfur dioxide reacting with more oxygen to form sulfur trioxide, which is a reversible process. And then for the Haber process, we're dealing with nitrogen gas reacting with hydrogen gas. Okay, these are the reactants, right, to form ammonia. All right, so these are very important as far as the IGCSE chemistry is concerned. So let's go to the next one, which is esterification. Of course, when you talk about esterification, it is one of the reactions in organic chemistry that is used to produce esters. Okay, the reaction you need to use to produce esters. And what you need is an alcohol. Okay, you need an OH.
Boy, it's just alcohol.
Okay, yeah, and you also need a carboxylic acid. All right, You need a carboxylic acid. You can see the functional, I'm simply writing the functional group here, but you know what I mean when I say OH is talking about an alcohol functional group. When I talk about the COOH, it's simply talking about
What a
a
sigma?
carboxylic functional group. All right, so the product of this reaction, okay, the reaction condition is that you need a catalyst, right? So the catalyst for esterification is concentrated H2SO4. And of course, you also need to heat it, all right? So you need concentrated H2SO4 here, and you need heat to make sure that the esterification reaction goes on, all right? And when you do that, of course, you form an ester, and water is also giving us as a product. So we are simply reviewing reaction conditions in this particular slide. All right, so that is for esterification, alcohol plus carboxylic. A catalyst is concentrated H2SO4, equally need heat. All right, let's go to reaction condition 5. Okay, hydration. Hydration simply means adding steam to an alkene. So you're adding steam to an alkene. Okay, so when you add steam to an alkene, you're going to form an alcohol. Okay, you're going to form an alcohol. All right. So what you simply need for the hydration reaction is you need a catalyst. Okay, an acid, which is a catalyst, which is phosphoric 5 acid. Okay, phosphoric 5 acid H3PO4 is needed for this reaction. You also need a pressure of about 6,000 kPa for this reaction to take place and a temperature of 300 degrees Celsius. All right, so you need to note this reaction condition for hydration. Okay, so you need a acid catalyst, which is phosphoric 5 acid. You need a pressure of 6,000 kPa, and you need a temperature of 300 degrees Celsius. You do not know which of these reactions you'll be asked on Monday. So it's good that you have all of this information properly arranged so that whenever anyone is asked, you can, give the correct responses to them. I'm going to entertain questions when I'm done with this, okay? So also remember that when you are dealing with hydration reaction, you produce an alcohol, and you can also have an isomer of the alcohol. For example, if you are having propene plus steam, you can have propan-1-ol. You can have propan-1-ol, and you can also have an isomer of propan-1-ol, which is propan-2-ol. Okay, so you could be asked, what is the product formed between propene plus steam, and give the isomer. So you should know that when you obtain propan-1-ol, you can equally have a propan-2-ol as the isomer. All right, so that is for hydration. So it means adding steam to an alkene. All right, let's go to hydrogenation. Now, hydrogenation means adding hydrogen to an alkene. All right, adding hydrogen to an alkene is different from hydration. Okay, and all of them are addition reactions majorly. Okay, so we have, for this case, you're adding alkene plus hydrogen. Okay, so alkene plus hydrogen. All right, so what are the reaction conditions for hydrogenation? You need a temperature of about 150 degree to 300 degrees Celsius. Okay, for hydrogenation. You also need, of course, we mentioned that you need hydrogen, right, added into the whole mixture. Okay, so this is the temperature that is needed for hydrogenation. All right, and when hydrogenation takes place, what you simply form is an alkane. So for example, if propene undergoes hydrogenation, it is going to form propane. Okay, if but1-ene undergoes hydrogenation, it's going to form butane. All right, so that is for hydrogenation, right? That is just, and of course, the catalyst for hydrogenation is nickel. You also need nickel as the catalyst for this process, okay? You need nickel as the catalyst for this process. So that is for hydrogenation, the temperature and the catalyst. All right, now let's talk about substitution. Now for substitution, it has to do with alkanes, all right? Alkanes undergo substitution, or we call it chlorination, basically. And this reaction takes place rather in the presence of UV light, okay? And that makes it a photochemical reaction. All right, it makes it a photochemical reaction. So any reaction that, takes place in the presence of UV light is a photochemical reaction. And also note, that the UV light supplies activation energy to the process. Okay. So the UV light simply supplies activation energy to the process. All right, so these are the basic reaction conditions that you need to know before going into, an examination. All right, so let's take questions on reaction conditions. Okay, I can see from the chat box. Okay, so esterification again. We're going to look at that. Now, somebody also posted oxidation. Good one. Thank you for reminding me oxidation. We're also going to talk about oxidation. Okay, so let's start with the first question about, let's start with the first question regarding, right, let's see, first one here is, okay, esterification. Now, I said esterification is simply a reaction, okay, for obtaining esters. Okay, we use it to produce esters. So esters, okay. And esters functional group, right? Let me just project this on a new page. Let me see, so that I can write. I think this is overloaded, right? So let me write on a new page. Okay. So esters, they kind of have this functional group. So for the esters, okay, let me write here. So for the esters, okay, for the esters, you kind of have C double bond OO, okay? So this is for the esters, all right? So we're saying that to form an ester, all you need is an alcohol, okay, plus a carboxylic acid, okay, using conc H2SO4 and heat, okay? So we're going to have ester, all right, plus water, okay? And remember that the carboxylic acid gives the OH, sorry, the OH here, while the alcohol donates the hydrogen to form water. So it is the H and the OH contribution that forms water. So in other words, we are saying that esters, you're going to have something like this as the functional group of esters, okay? So that is what we're trying to establish for that particular question. Okay, all right, so for oxidation, you're simply saying that the alcohol, okay, reacts with, oxygen atom, all right? So what supplies this oxygen is potassium manganate 7, right? This is what supplies the oxygen in the process of the oxidation. So this is more like the oxidizing agent. Okay, this is the oxidizing agent for the process of oxidation, all right? And of course, like I said, the oxidizing agent supplies oxygen while alcohol becomes the reducing agent. And whenever this happens, okay, we are going to have carboxylic acid as the result of the process of oxidation. So if you oxidize alcohol, if you oxidize propanol, you're going to have propanoic. Okay, you're going to have propanoic. So if you oxidize butanol, you're going to have butanoic. So that is the process of oxidation. For the person who asked the question of oxidation, I believe that has been clarified. All right, someone also mentioned something about what's the difference between substitution reaction and photochemical reaction. All right, so photochemical reaction is simply a reaction that takes place in the presence of ultraviolet light, or we could say sunlight. All right, so not all substitution reactions involve ultraviolet light. Okay, so photochemical reaction is just an example of one area of substitution. Okay, so whenever a reaction involves or a reaction takes place or it's initiated by light, we call such reactions photochemical. All right, and we see an example with the alkanes. Okay, alkanes undergo substitution reaction, such as chlorination, to form two products. All right, whether it could be chlorobutane and hydrochloric acid. All right, so photochemical reaction simply involves light, and I said what the UV light does is to supply the activation energy needed. All right, so that is the response to that question. Okay, so I've talked about fermentation. All right, so just can you repeat about fermentation? So fermentation, of course, is the breakdown of glucose. So the conditions for fermentation is, first you need yeast, which is like the enzyme, and then you also need it has to take place in the absence of oxygen. So when it undergoes that, okay, you're going to form alcohol and you're also going to form carbon dioxide. Yes, equation of incomplete combustion of methane. So complete combustion, what you need to know is that the complete combustion will give you carbon dioxide and water, while incomplete combustion gives you carbon monoxide and water. So that's the difference. So when you ask to write an equation of an hydrocarbon in undergoing complete combustion, you know the product should be carbon dioxide and water. But if it were incomplete combustion, you're going to have carbon monoxide and water. So let's write for methane like you have suggested, right? So we have methane, for example, undergoing incomplete combustion, that's with oxygen. The product should be carbon monoxide and water. And then we balance the equation. So one atom of carbon here, one atom of carbon here, 4 hydrogens, so we can put 2 hydrogens here to make it 4. All right, so there are 2 oxygens here, and there are 3 oxygens here. Okay, so since there are 2 oxygens here, and there are 3 oxygens here, we could simply say 3/2. All right, so we could simply say 3/2. And if we want to make it whole numbers, we can simply multiply by 2. We multiply by 2, we are going to have 2CH4 plus, okay, by multiply this by 2, this goes off, you're going to have 3O2, okay. Multiply this one by 2, you have 2 carbon monoxide. Multiply this by 2, we have 4H2O. So if you check now, you see that the reaction is balanced because we have 2 carbons, 8 hydrogens, 8 hydrogens, 6 oxygens, 6 oxygens. I believe I've answered the question of incomplete combustion of methane. All right, so paint show, I didn't get the aspect of the temperature used for what particular reaction. Okay, for what particular reaction. All right, now we want to solve past questions, but before we solve past questions, what we're simply going to do is to answer your question, because you are here for, I'm here to answer your questions. Okay, so just use the chat box and I'll be giving answers today. All right, someone said, can you do addition polymerization? Yes, we can do addition polymerization. All right, for addition polymerization, remember that one product is formed. Okay, and that's what makes it an addition reaction. Any addition reaction forms a single product. All right, any addition reaction forms a single product. So addition reaction majorly, we're looking at an alkene undergoing addition reaction. Okay, so I'm going to show you briefly how an alkene undergoes addition reaction and how we're going to form the polymer. Remember that polymers are formed by the addition of several units of monomers. Okay, so for instance, in a question, I think we could be asked to show how ethene undergoes addition polymerization. Okay, so this is ethene now, C double bond, C, H, 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 and H right here. So this is ethene undergoing addition polymerization. Okay, so when it undergoes addition polymerization, what happens is this double bond here breaks. Okay, so it breaks to a single bond. So we're going to have C single bond C, all right, and then you attach all the hydrogens that were there in the previous monomer, because this is the monomer now. So we are saying it undergoes polymerization. Okay, I'm going to let me draw a bracket to show that it's undergoing polymerization. Sorry, let's draw a bracket to show that several units of alkene, several units of the ethene are simply reacting. Okay, so if this undergoes polymerization, like I said, the double bond breaks, and then you have what's carbon-carbon single bonds, and then you attach the number of hydrogens that were there. So we had hydrogen up here, we had hydrogen right here, okay, we had another hydrogen right here, and we had another hydrogen right here. All right, so after doing that, the next thing, which is very important, is to include the continuation bonds. Do not just draw this. If you draw this, you're wrong, because this is not just a polymer. Okay, this is just, you just drew something incomplete. So you have to show that it's a polymer by adding continuation bonds. Add continuation bonds to the left and right, and this is now a polyethene. Okay, so this is now a polyethene, and then you get your full marks. So the essence of in addition polymerization, you are forming a single product, And it simply deals with the breaking of the double bond to form single bonds and the adding of the continuation bonds. Now, I'm going to solve another question now, which is from a past question, which most students do not, which most students fail. All right, so the question is, draw the polymer of butene. Okay, butene. All right, we want to draw the polymer of butene. Now, most students will draw butene and claim it is butene. So you have to know how to draw butene and butene. All right, so remember that the general formula for alkenes is CnH2n. Okay, so butene is going to be C4. Butene is butene or butene, 1N of butene is going to be C4H8. Okay, because N is 4. Now, I want to draw butene. So I'm going to draw 4 carbon atoms first. 1, 2, 3, 4. So after drawing the 4 carbon atoms first, I remember that the double bond is on the second. Okay, it has a position 2. So position 2 here is going to be, if you number it forward, let's say we are numbering forward, 1, 2, 3, 4. So position 2 is going to be here. All right, position 2 is going to be here. Okay, for butene. If it were butene, then it has to be on the first carbon. What we are trying to do for butene. So after putting the double bond, the next thing is to attach all the hydrogens that should be there. So I'll attach hydrogen here, right here, right here. Okay, and I'll equally attach hydrogen right here, hydrogen right here, hydrogen right here. Now, remember that the number of bonds that should be attached to carbon should only be 4 because carbon has a valency of 4. So if there is 1, 2 already, there's 1 here already. So I only need to put 1 here. So that becomes 1, 2, 3, 4. All right. The same thing applies here. 1, 2, 3, 4. So this is the structure of butene. Now that I know the structure of butene, let me now transcribe it into a way that will be easy for me to draw the monomer and polymer of butene. So I'm going to convert this structure now into something that is going to be really easy to see and draw. So if you have a question like this again on Monday. All right, so look at what I'm going to do now. I want to transcribe this. I want to move, let me use a different marker now, different color. I want to move everything here. I want to make it look like 18. I want to make it look like 18. So all I need to focus on is this point. So I'm going to draw this one now. So it's going to be C double bond C. All right, and I'm going to attach H right here to the first carbon there and the H right here. So what I've done is I've drawn this middle one because this is our focus. This is where the breaking will occur if there's going to be breaking for it to form a polymer. Now I'm going to look at carbon 2 now. What was attached to carbon 2 on the left? All right. So if you look at what was attached to carbon 2 on the left, look at what was attached to carbon 2 on the left. CH3. So CH3. So I'm going to go up here and write CH3. All right. Then I go to the other wing. I see carbon 3. What was attached to carbon 3 on the right? Another CH3. So I'm going to put CH3 again. Okay, so CH3 again, right here. So what I've simply drawn is butene. So I've converted butene to a structure that will be easy for me to draw the polymer. All right, and just like I said about drawing polymers, all we need to do is to break this bond, break the double bond. So I'll just do the same thing, break that double bond there, I have carbon, single bond, carbon. All right, now that I have carbon, single bond, carbon, what was attached to the first carbon? So this was the first carbon. What are the groups attached to it? We had H below, and we had CH3 right up here. Okay, and I look at what was attached to the second carbon, it's still CH3 again, and I also have H right here. Okay, or we could alternate this as the case may be. So it doesn't matter. I could simply do something like this. It's still the same thing. I could do it like this, and I'll still get the same result. I could alternate it and put a CH3 down here instead, and put a H here. It's the same thing. All right. So after doing this, remember the next thing then is to draw continuation bond. So I'll just put the continuation bond, and I'm good to go. So this is a repeat unit of polybutene. Okay, so this is one of the repeat units of polymerization. I could keep on repeating this again to form several repeat units. And that is what addition polymerization is all about. You form a single product. So I believe I've explained enough on addition polymerization. Okay, Fayed talks about polymerization. So apart from addition polymerization, we also have condensation polymerization. Okay, for condensation, we've reviewed addition. Okay, we've reviewed addition polymerization, which has to do with majorly an alkene. All right. So and remember that addition polymerization forms a single product. So for condensation polymerization, you're going to form you're going to form a polymer, and you're equally going to form a small molecule such as water or hydrochloric acid in some cases. All right. So for condensation, we are looking at two major examples according to your syllabus. We are looking at a polyamide and we are looking at a polyester. So these are the two that you likely find as far as condensation polymerization is involved. So a polyamide also looks at the natural polymer, which is a nylon. Right. So I'm going to erase this and show how some of the condensation polymerization takes place. All right. So let's start with the polyamide. Let's start with the polyamide. All right, so for the polyamide, they are majorly from two functional groups for the polyamide. So I'm just going to draw something very easy. Okay, so we have a diamine. So a polyamide is simply from a diamine, right? A diamine plus a dicarboxylic. Okay, so a diamine plus a dicarboxylic. So this is what is going to form you a polyamide. Okay. Okay, so this is what is going to get you a polyamide. Okay, so we're simply going to draw the linkage of the polyamide. So how do you identify a polyamide linkage? Right, so the carboxylic acid there would give out the OH, while the diamine gives out the H. So what you're going to see basically as a linkage for the polyamide is C double bond O and H. So this is what you look out for a polyamide link. Okay, C double bond O
Mister, what's a
and
diamine?
H. Yeah. What do you mean by? I didn't get the question.
Yeah, Mister. So what's a diamine? I forgot.
Yeah, a diamine is two amine groups. Di means two, so amine group is NH2, right? So this is an amine group. So when you have two of an amine group, we call it a diamine. All right. So this, because it has two amine groups, we simply call it a diamine. All right. So this is what you would form. This is the linkage for a diamine, and of course, water is eliminated. So for every linkage, water is eliminated. So if you have two linkages like this in your polymer, that means two water molecules have been given off. If you have three of these, that means three water molecules have been given off. If you have four of these, that means four water molecules have been given off. All right, so this is a polyamide. So this is a polyamide. So if you see any of this, it's a polyamide. It's also similar to we also call it nylon, and it also has a similar linkage to protein. So protein also have this similar polyamide linkage. All right, so this is very important. So note this and review it if you've not done it. Now let's talk about the second condensation polymer that we would find in the exam question. And that second polymer is polyester. So polyester. So I'm simply going to use a different marker as well. So polyester, right? So we could also have a polyester. Now, a polyester is formed from a diol. So I'm going to draw a diol now. So a polyamide is from a diol. So this is a diol plus a dicarboxylic. All right, so a dicarboxylic. So this is dicarboxylic. Okay, so you're going to form, this is going to be the linkage, COO. So whenever you see this, okay, this is a the poly or the ester linkage rather. So this is the ester link. Okay, so which forms the polyester. So this is the ester linkage, and of course there is an elimination of water. So if you have one of these, that means one water molecule is eliminated. If you have two of these, that means two water molecules are eliminated, and you could go on like that. And then we have the protein, okay, which is also a condensation polymer. All right, I think I've reviewed enough for that of polymerization. Okay, someone asks, and for precipitation reaction, right? Let's see this. It says for precipitation reaction, is it always made up of soluble reactants? Yes. For you to form a precipitation reaction, precipitation reaction is used to produce insoluble salts. Okay, so for you to produce insoluble salts, you need two soluble salts, all right? And I have a very simple way of learning the soluble salt. So I'm just going to share that immediately. Soluble salt. So if you want to learn the soluble salt, let me go to another page. Right, I just need to erase this. So if you want to learn the soluble salt, there is a simple way of going about the whole thing. There is what we call this acronym for soluble salt, SNAP. Okay, so let's just see how we could do that quickly. So you want to learn soluble salts, you say SNAP. So soluble salts. So SNAP. All right. So SNAP simply means all sodium nitrates, ammonium, and potassium salt are soluble. Okay, so you just need to have this at the back of your mind. So if you want to form a salt via precipitation, you need to pick a salt from this category. You have to pick out the soluble salt, okay? Dealing with the soluble salt, you pick them out from here. So all sodium nitrates, ammonium, and potassium salts are soluble. So that's for soluble salts. Now let's go for other parts of the salts and see how you can identify insoluble salt as well. So if we know that all sodium nitrates and potassium salts are soluble. Right, so let's look at chlorides. What are the chlorides? Yeah.
What's H20?
That's water, okay? Where do you see H20? Okay, so chlorides, all right. So chlorides, we have PaH. All right, so lead, silver, and mercury. So chlorides of lead, silver, and mercury are insoluble. Okay, these ones are insoluble. Okay, so salts of lead, silver, chlorides of lead, silver, and mercury are insoluble. Then we also have the sulfates that are insoluble.
Sir.
We have a V. Yeah.
Isn't Mercury a planet?
We have mercury as an element, okay, which is Hg, right? So, all right, so we have calcium and we have lead as well. Okay, so these are the sulfates that are insoluble. Okay, these are the sulfates that are insoluble. So barium, sulfates of barium, calcium, lead are insoluble. Okay, and then we talk about carbonates. So for the carbonates, only the sap, we have sap to remember that. Okay, so for carbonates, only sodium carbonates, ammonium carbonates, and potassium carbonates are soluble.
Sir, what is
okay,
salt? So, what is salt?
I just gave, so you can see it on the screen, all right? S represents sodium, A represents ammonium, and P represents potassium. So for the person asking a question on precipitation reaction, so you need to pick soluble salt, two soluble salts, to form a precipitate, all right, to form an insoluble salt. Okay, yeah, someone mentions test for sulfur dioxide gas. All right, all you need is, the potassium manganate 7. Okay, you need the potassium manganate 7 to decolorize. Okay, that's very, very easy to check under the test too. All right, someone is saying, will your paper be hard? Okay, I do not set papers. Okay, I only help you to appreciate the knowledge and direct you to areas you need to review. UV light used to speed up the rate of reaction. UV light supplies the activation energy. Okay, it supplies the activation energy needed for the reaction. For the notes on fermentation, of course, you can read from your textbook. You have
hello, sir. I have a question.
Yeah, go ahead.
So for the 2n cube plus minus 16 squared solution, what do I use?
Okay, I think that guy needs to be kicked out. Okay, he needs to be kicked out of the class. All right, so yes, Zed was saying, can you tell us like basically most important stuff to know well? Yeah, these are the most important stuff we are talking about here. All right, so just pay attention. Everything we say here is very important. How do we know where to add the double bond? Yes, but 1 in and but 2 in are the same. Okay, they are the same. How do you know when to add the double bond? It depends on the number you're giving. So if it is but 1 in, the double bond should be on the very close to the first carbon. If it is but 2 in, the double bond should be close to the second carbon. Are you going to share the 2024 May June paper? No, I do not have the 2024 May June paper. I can only predict certain questions that you should expect. States of matter, really? Okay, anaerobic simply means absence of oxygen. Okay, someone saying you have to draw 3 repeat units. Okay, let's go back to that point. Where do we have question or repeats? Okay, so let me just erase this so that I could show
Can
how
you
to
read
draw.
it?
Okay, so let's see how we could draw the repeat units. So for instance, if I want to draw 3 repeat units of ethene, okay, I want to draw 3 repeat units of ethene. All I need to do is, ethene has this structure this way. So C double bond, C, H, 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 H. Okay, so it's a polymer this time. So I want to draw 3 repeat units. This is the first repeat unit. So H, H, H.
Mr. Why aren't
H.
there double bonds in the addition polymerization?
Yeah, it's additional polymerization we're doing, right? So we have the second repeat unit. Just repeat, keep on repeating what you have in the first one. So H, H. Okay, and I could also have a third one. Okay, right there. Then if you're having 2, so what I have in this case, I'm drawing 2. So you could draw 3. If you could draw 2, you could draw 3. So it's not really difficult. So what I've done is I've done 2 repeat units. Then what I need to do to make sure I get all the marks is to add the continuation bond. If you do not have the continuation bond, you will lose some marks, or you might just lose the whole question. So be careful to add the continuation bonds to the question. Okay, yes, someone said extraction of iron. Solubility chart already, right? So I'm just going to talk about extraction of iron. Yes, thank you very much for bringing us to this. This is the next part. Remember, I said you have to know reaction conditions. You have to know the conditions for every reaction. You have to know the salts that are soluble and insoluble. Now, we're going to look at extraction. You have to know extraction. There is no way you go into a chemistry examination without knowing the extraction of the 2 major metals, which are aluminium and iron. So I'm going to quickly run through the equations for the extraction of both aluminium and iron. And if we do this revision, you'll be able to answer any past question, because I have the experience of all the various angles of the questions. So I will just incorporate everything as I'm explaining. All right, so let's go straight. So I'll just write iron here, and I'll write aluminium on the other end. Okay. So first thing is to know the ore that is used for the 2 processes. So for iron ore, okay, the ore you need is for iron is simply the hematite. So this is the ore needed for iron. The ore needed for aluminium is bauxite. Okay, and the formula of the iron ore is Fe2O3, is Al2O3. So that's the first thing you need to know. Now, the process for the extraction of iron is using the blast furnace, right? You use the blast furnace for the extraction of iron. Okay, while for the extraction of aluminium, we use electrolysis. Now I'm going to explain something. Sometimes the IGCSE chemistry questions will ask you, why can't you use blast furnace for aluminium? Now, why we can't use blast furnace for aluminium is because aluminium is far more reactive than carbon. You know, what we use in the blast furnace is reacting iron with more of carbon, which is coke. And that's because carbon is more reactive, or is higher on the reactivity series than iron. But in the case of aluminium, aluminium is way higher on the reactivity series than carbon, which is more reactive than carbon. And that is why we cannot use the blast furnace to extract aluminium. This is a common question in IGCSE chemistry. Why can't aluminium be extracted using the blast furnace? Simply because aluminium is more reactive than carbon. So carbon cannot reduce aluminium. Okay, so apart from the hematite as the ore, there are other materials that are added to the ore, such as coke. Okay, hot air is introduced into the blast furnace. Okay, you also introduce limestone into the blast furnace. All right, so what you simply introduce into the process of aluminium on this. So why do you introduce cryolite? Number one is to reduce the operating temperature. This is very important. Reduce the operating temperature. That is why you add the cryolite. And secondly, to improve conductivity. Okay, you add the cryolite to improve conductivity. These are very important, okay? To reduce the operating temperature and to improve conductivity. You have questions like this. This is what you should write on why cryolite is added. Okay, so let's go over to see what then goes on in this process. Okay, so the first reaction is that the coke that you added reacts with the hot air to form carbon dioxide. Okay, then secondly, the carbon dioxide further reacts with more of the coke to give carbon monoxide. Okay, to give carbon monoxide. All right, and then step number 3 is this carbon monoxide has been produced, simply react with the iron ore. Okay, it reduces the iron ore to form iron plus carbon dioxide. Okay, and of course you can balance this equation, right? It's important that these equations are balanced. So there are 2 ions here, so there are 2 ions here. There are 4 oxygens here, so I could basically put 2 here. Okay, and then put 2 here. Okay, so if I put 2 here, right, sorry, let's balance this. Okay, so we could balance this just because of time. All right, so when you form the ion here, remember that you added limestone. There are impurities in the whole process. So the calcium carbonate goes through thermal decomposition to form calcium oxide as a carbon dioxide. Okay, goes through thermal decomposition to form calcium oxide plus carbon dioxide. And then the feed process is this calcium oxide, okay, reacts with the impurities in the ore, which is silicon dioxide, to form the slag, okay, which is calcium silicate. Now, let's review what happens in this process. Some questions will ask you, why is coke added to this blast furnace? So coke is added to supply the heat. Okay, we have that in 2024 paper where a question was asked, February, March 2024, why is coke added? Or why is carbon used? So it's added to supply heat to the whole system. Okay, so you could also be asked, why is limestone added? So limestone is added to decompose into calcium oxide, which reacts with impurities. Okay, so this reaction 5 is an acid-base reaction. It's an acid-base reaction because it is a metal oxide, which is a basic oxide, plus a non-metal oxide, which is an acidic oxide. So we could be asked, why is equation 5 an acid-base reaction? Because it involves a reaction between a basic oxide and an acidic oxide. All right? It could equally be asked that why is a carbon introduced? I've answered that already, to supply it to the system and to also form carbon monoxide, which reacts with the iron ore. All right, so that is for iron. I think those are the major questions you have as far as iron extraction is concerned. Now, let's talk about aluminium now. Aluminum is extracted through the process of electrolysis. And when you talk about electrolysis, this is carbon, okay? It's carbon. All right. So you can be asked to write what happens at the cathode or what happens at the anode, because since we are talking about electrolysis, we're simply talking about an electrolyte, a cathode, and an anode. Okay, so the electrodes used in the process of extraction of aluminium are simply carbon electrodes. Okay, they are carbon electrodes that are used. So at the cathode or at the anode, remember this is the electrolyte, aluminium, okay, aluminium oxide. So at the cathode or at the anode, let's start with the anode reaction. Oxygen goes to the anode. So we're going to have O2 minus, okay, losing electrons, O2 minus losing electrons to form oxygen gas plus the electron that is lost, okay? And we can simply put a 2 here to ensure that, okay, we can have a 2 here to ensure that the equation is balanced. So let me balance this properly. So, okay, so first we are writing what is occurring at the anode. Yes, you should know what is occurring at the anode. Okay, so we have 4E minus, because there are 2 oxygen atoms and there are 2 oxygen atoms, then 4, charge of 4 and charge of 4. So this is what is occurring at the anode. And at the cathode, the aluminium ion receives electrons to form the aluminium metal. Okay, so we balance this by putting a 3 here. Okay, so this is what is happening at the cathode as far as this reaction is concerned. And the aluminium gotten is in the molten state. So it could be asked, why is the aluminium gotten in this process? Why is it in the molten state? It's in the molten state because that's for iron, not aluminium. Okay, so the ion gotten in this case is in the molten state because the temperature of the blast furnace is above the melting point. It is above the melting point of the iron. So that is what you simply have as far as extraction is concerned. I think I've answered most of the questions. Yeah, there's another question that involves, why do you keep on replacing the electrodes in the electrolysis process? Remember, the electrodes is carbon or graphite electrodes. So the oxygen gas produced at the anode reacts with the carbon electrodes to form carbon dioxide, and that goes off as a gas. So you need to keep on replacing of aluminium, because the oxygen gas produced at the anode simply reacts with carbon to form carbon dioxide, which goes off as a gas. So you need to keep on replacing the anode, and that's what makes this process a complicated one. So that is all for the extraction. I believe I've answered every form of question that could come out from extraction. Okay, for precipitation, remember precipitation is for insoluble salt. For titration is majorly for soluble salt. So I'm going to quickly do something here to explain that briefly. So for precipitation, you're trying to prepare an insoluble salt. For titration, you are preparing a soluble salt. Okay, so I'm going to do a simple comparison here so that we can move forward from that. Okay, I think we need to mute everybody so that we only use the chat box. Okay, if it's possible to mute everyone so that the chat box is the only means available for people to ask questions or participate. The moderator should ensure that, please. If it's possible, you mute the. Okay, so this is majorly for insoluble salt, and this is majorly for soluble salt. All right, so for precipitation reaction, step number 1 is mix the 2 solutions of the soluble salt. Okay, you have 2 soluble salts, so mix them together, mix the solutions. Step number 2, filter the mixture. Okay, because when you mix the 2 solutions, you form your insoluble salt, you filter to obtain the crystals of the salt, then you wash with distilled water, and then you dry. Wash with distilled water, and then you simply dry in between filter papers. So dry in between filter papers. So this is how to prepare insoluble. This is the template for preparation of insoluble salts. But for titration method, first step is to add activated charcoal, or add activated charcoal to remove the indicator. Okay, so the essence of adding activated charcoal is to remove the indicator. All right. So step number 2, after adding activated charcoal to remove the indicator, is to heat to point of crystallization. Heat to point of crystallization. Okay, so heat to point of crystallization, then you can filter, right? And then step number 4 is after filtering, you wash with distilled water and you then dry. So wash with distilled water and you dry. So you can see that the steps for insoluble salts is different from the steps for titration. So what you need to do is to add activated charcoal first to remove the indicator, because in titration, you have added an indicator, whether methyl orange or phenolphthalein, then you've gotten your endpoint. So you need to, review it by by adding activated charcoal. Then you heat to point of crystallization, you filter, you wash with distilled water, and you dry. So that's the difference between the two processes. I believe I've answered that question there. Okay, so what are your predictions for May, June? Yeah, prediction for May, June is simply the same predictions for every paper. There are certain questions you cannot omit. Electrolysis is one of them. Salt preparation is one of them. Okay, rate of reaction is one of them. Using the Le Chatelier's principle is one of them. Okay, and organic chemistry, of course, is always there. Polymers, always there. So the same prediction, bonding, whether ionic bond or covalent bond, you'll be asked to, draw one of them, right? Given a compound, and you're asked to fill in the electrons, those are questions that will definitely be there. So we have bonding, we have rate of reaction, we have, salt preparation. We all equally have organic chemistry. Of course, you also have some questions on chemical energetics. Okay, you could be asked to find the bond energy. So that's another area you need to go and revise if you've not done that. And then there are some questions that could come maybe from the paper 6, questions on experimental techniques, right? Such as tests for oxygen, tests for hydrogen, all right, or tests for the carbonates, as the case may be. So review that. You could also have maybe some questions on flame test. All right, so we need to also review flame tests to be sure that you are prepared. And then you also need to look at, I mentioned electrolysis already, chemistry of the environment, test for water. Okay, test for water, how the catalytic converter works is another area you might need to look at. Okay, the equation for a catalytic converter, all right, some of the greenhouse gases, and how to solve the problem of the greenhouse gases. So these are some areas that, questions will come out. Of course, periodic table, you definitely have some questions on the periodic table to apply. All right, and what else? States of matter. Okay, we've not really had much question on states of matter, but you could see them this time. So it's just simply the same pattern. Look at February 2020, look at February, March 2023, look at May, June 2023, look at October, November 2023, look at February, March 2024. You could get the pattern to expect in the exam. So I think I've answered the question on predicted questions. I said something about rate of reaction, reaction conditions, Haber process, contact process, right? Remember the old equation for the contact process, including the formation of oleum. So you need to review that. Okay, a question could be asked to write the old equation for the contact process, okay, and how you obtain oleum. Why is water added, okay, to the fourth process? So these are things that you are going to have. Okay, so zinc extraction is not in the syllabus. Can you say you add cryolite for less melting point? Well, that aspect, the examiners have corrected that instead of saying you add cryolite for less melting points, rather say that cryolite is added to reduce the operating temperature, okay, of the reaction. So to be on the safer side, let's go with what the examiners want, okay, which is to reduce the operating temperature of the process, or you could say to improve the conductivity, okay? No, the crown light is not used as an electrode. No, it is kind of supporting, is added to support the process or the breakdown of the electrolyte. Okay, I already gave the ionic equation already. No, you don't have to memorize the chemical formula of cryolite. Okay, that's not what the syllabus wants you to do. Limestone is added to the blast furnace for it to decompose, right, and produce calcium oxide, which then, helps you remove the impurities. Okay, so I think I've answered. Okay, all right. Okay, what is not in the syllabus? Zinc is no longer in the syllabus. Okay, you don't have to read extraction of zinc. You equally do not have to read carbohydrates, because carbohydrates equally is not there. Yes, somebody mentioned something about desulfurization. Yes, desulfurization is a process we use, in for the oxides of sulfur. Yes, and in the process of desulfurization, what you simply add in the process of desulfurization is calcium oxide. Okay, yes, the fluid desulfurization is important. Okay, it is one of those questions you can tell will come out. Expectation for Monday's exam, I already said that. Read rate of reaction properly. Remember, yes, I wish I could let me quickly do this before we round up this class, especially on rate of reactions. So, most students make the mistake when you increase the concentration of the acid, it doesn't change the volume of gas produced. Please note that. Okay, it is only the change in concentration or mass of the solid that will change the volume of gas. Okay, so please note that changing the concentration of the acid
I have a question.
does not necessarily change the volume of gas. If you have a question, please post it on the chat. All right, if you have a question, post it on the chat box. Thank you. All right, so I think I've answered that question. Okay, so let's see. Yes, equilibrium and reversible reaction. Okay, let's do that quickly. Equilibrium and reversible reaction. So yes, two definitions of equilibrium. Very important. How do you know a reaction is at equilibrium? Number one, the rate of forward reaction, okay, is equal to the rate of backward. That's the first description of a reaction at equilibrium. Rate of forward reaction is equal to the rate of backward reaction. And then for two, concentrations of reactants and products, are constant. Now you need to be careful here. When we say concentrations of reactants and products are constant, it doesn't mean they are the same. It simply means the concentration of reactants and products are no longer changing. That is, they remain steady. Okay, so do not say concentration of reactants and products are the same. Because if you say they are the same, you are saying that the concentration of reactants is 2, concentration of products is equally 2. No, that's not what it means. It's simply saying if the concentration of reactant is 2, it doesn't change. If the concentration of the product is 3, it doesn't change. And these are the two things you need to write when you are asked to describe what is a reaction at equilibrium. Okay, so this is very important. We have repeated questions on this to describe equilibrium with 2 marks allocated. So you have to write that the rate of forward reaction is equal to the rate of backward, and then the concentration of reactants and products are constant. That is, they are no longer changing. All right, so let's briefly apply Le Chatelier's principle to understanding reaction process. When we talk about Le Chatelier's principle, we're talking about 3 factors. We talk about concentration, we talk about pressure, and we talk about temperature. So you have to understand how Le Chatelier's principle is explained using each of these factors. So I'm going to use the EBA process, which is nitrogen plus hydrogen, a reversible reaction to give ammonia. All right, so I'm going to put 3 here. All right, so these are gaseous reactions, remember. And from your study, remember that this is an exothermic reaction. Exothermic. So exothermic reaction. Change in enthalpy is negative. All right, now we have to explain using temperature. So because this reaction is exothermic, when you're asked to explain now, you need to know when the question is talking about rate of reaction and equilibrium. They are two different things, okay? So you need to read your question carefully. Is the question asking you to tell how temperature affects the rate of reaction? Or is the question asking you to say how temperature affects the equilibrium position? Now, if you're talking about how temperature affects the rate of reaction, for 3 marks, listen carefully. For 3 marks, 3 things to talk about. So for 3 marks, there are 3 things you need to talk about on how temperature affects the rate of reaction. I'm going to list out those 3 things to get you your 3 marks. Now, number 1, you have to talk about the fact that the particles gain energy. Okay, so you have to buttress the fact that the particles gain energy. Then secondly, you have to mention that because the particles have gained energy, there's an increase in the frequency of collisions. So talk about the increase in frequency of collisions. That's how to get the 2nd mark. And then to get the 3rd mark, which is always a 3 marks question, it's a 3 mark question. So to get the 3rd mark, talk about activation energy, that there are more particles with energy equal or greater than the activation energy. So talk about the activation energy. So when you're asked, how does temperature affect the rate of a chemical reaction? If it is increase or decrease, speak about that the particles gain energy if it's an increment. And because they've gained energy, these particles will collide more frequently. And then there are more particles with energy equal or greater than activation energy. So this is how to get the 3 marks when you're explaining how temperature affects the rate of reaction. But in terms of equilibrium now, how does temperature affect equilibrium? What you need to consider is whether if the reaction is endothermic or if the reaction is exothermic. So if the reaction is endothermic, if you increase the temperature, equilibrium shifts to the right. So if the reaction is endothermic, if you increase the temperature, equilibrium shifts to the right. Note this. But if the reaction is exothermic, if you increase this temperature, equilibrium shifts to the left. So if you want to use temperature to interpret equilibrium position, what you need to confirm first is the reaction endothermic or is the reaction exothermic? If it is endothermic, if you increase the temperature, equilibrium shifts to the right. If it's exothermic, if you increase the temperature, equilibrium shifts to the left. That is the principle you need to hold on to as you go into an exam. So we are done with temperature. Okay, we are done with temperature. That's just the analysis of temperature. Okay, so for temperature, it's dependent on if the reaction is exothermic or if the reaction is endothermic. All right, now let's go to pressure. Now, pressure is not dependent on whether it is endo or exo. No, pressure is dependent on the number of moles reacting and the number of moles of product formed. Okay, so for pressure, all you need to do is to calculate the number of moles of the reactant and calculate the number of moles of the product. So if I want to calculate the number of moles of reactants, I'll say 1 plus 3. So in this case, there are 3 moles for reactant total. And then for product, just 2 moles. Okay, so increase in pressure will favor the side with lesser number of moles. I repeat, increase in pressure will favor the side with lesser number of moles. So if I increase the pressure of this reaction of the Haber process, okay, equilibrium will shift to where there is lesser number of moles. So 2 moles is on the right, 3 moles is on the left. Since there are lesser number of moles on the right, equilibrium shifts to the right when I increase the pressure. But when I decrease the pressure, equilibrium shifts to the side where there are more moles. So where there are more moles is simply here. So equilibrium shifts to the left. So in summary, for pressure, increase in pressure favors the side with lesser volume. Okay, so if you are asked to state how pressure affects equilibrium, first talk about where the equilibrium shifts to. Is it shifting to the right or is it shifting to the left? Then the second mark, you talk about why is it shifting to the right or the left, which has to do with the number of moles. These are very important information. Like remember, when you are discussing temperature, equilibrium shifts to the right or the left because the reaction is endothermic or the reaction is exothermic. You get your 2 marks. For pressure, equilibrium shifts to the right or the left because the number of moles is more or the number of moles is less. These are the reasons you need to state. I believe this information is clear enough. So for temperature, we are looking at if it is endo or exo, and you have to tell us where the equilibrium shifts to. And the reasons why it is shifting to that angle is because it's either endothermic or exothermic. For pressure, you tell us where equilibrium shifts to, and you tell us that the reason why it is shifting is because of the number of moles. Where are there more moles or where there are lesser number of moles? So these are the 2 things you need to consider. Then for concentration, all right? Concentration is the easiest, okay? When you increase the concentration of a reactant, for instance, equilibrium shifts, okay, to the right so that more products are obtained. Okay, so you need to know that when you increase the concentration of a reactant now, there are more products. So concentration is very easy, and I don't think we should have any problem with increasing or decrease in concentration. All right, so I think I've explained enough on that, on equilibrium and reversible reactions. All right, so hydrogen cells, good question. Hydrogen cells is very simple for hydrogen cells. What you need to know about hydrogen cells is the equation for hydrogen oxygen fuel cell, right? What is the equation for the hydrogen oxygen fuel cell? That's what you need to know about that. And what are the advantages and disadvantages of hydrogen oxygen fuel cell? So it's really easy. So for the hydrogen oxygen fuel cell, remember that the general equation, the overall equation is H2 plus O2 to form H2O. So this is the approved equation for hydrogen oxygen fuel cell, all right? And this is what you should write when you're asked to write the equation for hydrogen oxygen fuel cells. And you know, the advantage of the hydrogen oxygen fuel cell is the fact that there's zero emission of toxic gases, okay? That's one advantage, zero emission of toxic gases, all right? And of course, it is very renewable if you are sourcing for the reactants from solar. Okay, but the disadvantage of the hydrogen oxygen fuel cell is that we do not have enough filling stations that can dispense these gases. And then secondly, it is expensive, right? You have to do an engine redesign to be able to make use of this. But it is very environmental friendly, it's non-toxic, okay, and those are some of the advantages of it. So I believe I've talked about hydrogen oxygen fuel cell. Right, the electrolyte in hydrogen oxygen fuel cell is most times sodium hydroxide or potassium hydroxide. Tests for anions and cations are very easy. Okay, just go over your papers, experimental techniques. Remember that for chloride anion, you are simply adding dilute nitric acid and silver nitrate. If you add dilute nitric acid and silver nitrate, you have a white precipitate. That's for the chloride ion. Okay. For the bromide ion, you have a cream precipitate. And for the iodide ion, you have a yellow precipitate. So you are simply adding the same set of reactants for the halogens. I repeat, for the chloride ion, you are adding dilute nitric acid plus silver nitrate. So you produce a white precipitate. For the bromide ion, the same thing, you add dilute nitric acid plus silver nitrate, you produce a cream precipitate. So this one produces a white precipitate. The bromide ion produces a cream precipitate. And the iodide ion produces a yellow precipitate. So what we are adding is dilute nitric acid and silver nitrate. We use this to test for all of this. All right. Okay, so that is for the anions. For the nitrate ion, if you are testing for nitrate ion, okay, you're adding nitrate, you want to test for nitrate ions, you're adding aqueous sodium hydroxide with the aluminum foil, all right? And then what happens is you use a damp, okay? You use a damp damp red litmus paper, because you're going to form ammonia. In the test for nitrate ion, you're going to form ammonia, and when you use a damp red litmus paper, it turns blue, because ammonia is an alkaline gas, so it turns red litmus paper blue. So that is the test for the nitrate ion. When you're testing for nitrate ion, you produce ammonia, and this is what you need to do to test for it. If you are testing for a carbonate, all you need to do is to add acid. When you add an acid, you simply form carbon dioxide gas, which turns lime water milky. Okay, which turns lime water milky. Okay, and then for hydrogen, test for hydrogen gas. When test for hydrogen gas, you need a lighted splint or a lit splint, and the result is it gives a squeaky pop sound. You're testing for oxygen gas, you need a glowing splint, and the glowing splint will ignite. Okay, so these are just the basic tests you can do. So somebody mentioned something about electroplating. Now, electroplating is simply the coating of a metal with another metal. Now, two reasons why electroplating is done. Please take note, the person who asked this question and every other member of the class. The two reasons why we electroplate is, number one, to make the material resistant to corrosion. Okay, make the material resistant to corrosion. That's one. And then secondly, to improve the appearance. That is why you electroplate. All right. So some of the metals we use in electroplating are silver, nickel, chromium. All right. So we do this, two reasons. IGCSE chemistry question can ask you, what are the two reasons for electroplating? Is to make it resistant to corrosion and to improve the appearance. Now, when you are electroplating, you need an electrolyte, and the electrolyte must contain the same metal you want to use in electroplating. I repeat, the electrolyte must contain the same metal you want to use in electroplating. So let's give an example. Probably I want to electroplate spoon. So I want to electroplate spoon with silver. So silver will simply be, I want to electroplate spoon with silver. So this is my spoon. All right, I want to electroplate this with let's just draw something basic. I want to electroplate this. All right, so what will simply occur is that this is silver, okay, and this is the spoon. So when you are electroplating, this material you are trying to protect should always be at the cathode. For electroplating, the material you're trying to protect should always be at the cathode, while the metal that is used in protecting the other metal should always be at the anode. Okay, so the metal I want to use to electroplate should always be at the anode, because loss of electrons occurs at the anode, while the metal or the material I'm trying to protect should always be at the cathode, because gaining of electron occurs at the cathode. Now, the electrolyte must contain the metal, which is silver nitrate. I have to use an ionic compound that contains the metal I want to use to electroplate. So these are the things you need to know about electroplating. So remember that the metal you want to use in electroplating must be at the anode. The material you are trying to protect through electroplating must be at the cathode. The electrolyte must contain the metal that you want to use to protect. That is why it is silver nitrate, and it has to be an ionic compound, because only ionic compounds are suitable electrolytes. I think I've answered the question on electroplating. Remember the two reasons why you electroplate.
Please, can you write the half equations?
Okay, half equations, all right. So let's write the half equation for the process of electroplating. So the first one is the silver metal loses electron to form this, all right? And then on the other end, there is a gaining of electrons from the same spoon, which is, there's a gaining here, to produce silver on the surface. So this is the anode, half ionic equation at the anode, and this is the half ionic equation at the cathode. All right, so I believe I've answered your question. All right, so let's see other questions. Bond energy and how to calculate it. Oh, the class is about ending. I'm supposed to end this class by 8:30. Enzyme, what kind of enzyme? You don't have enzyme in your syllabus. Okay, so enzyme is not discussed here. Exothermic or endothermic? Okay, let's briefly look at that. I'm going to end this class exactly by 8:30 because I have other things to do, right? So I'm going to just entertain questions. But if you have further questions, you could post it on the Discord channel where there's chemistry, and I'll try and give answers to some of them. Right, that's what I could do to ensure that I try and help as much as possible. All right, so I want to talk about okay, so I'm going to quickly talk about stoichiometry. All right, but I might not be able to calculate bond energies because I have to look for a question. Or maybe if I can quickly find a question, I'll talk about it. But for stoichiometry, these are the formulas you need to know. We talk about solutions, we talk about solids, and we talk about gases. Okay, so number of moles in solution is concentration over volume. Sorry, let me write this. It should be the other way around. So number of moles for solutions. So remember that concentration is number of moles over volume. So number of moles is concentration times volume. Number of moles for solids is mass divided by the molar mass. Number of moles for gases is simply volume of the gas divided by 24 dm cubed. Okay, so I'll see if possible I could solve questions before, or I could just add about 5 minutes to solve some questions on this. Then if you're asked to find number of moles in terms of particles, there's going to be number of particles, right? Number of particles divided by 6.02, which is Avogadro's constant. So these are the formulas you need to know for number of moles. So you have to know, while we're talking about solutions, are we talking about solids? Are we talking about gases? Or are we talking about number of particles? Remember that when you're solving number of moles in terms of solution, it has to be in mole, the concentration is in mole per dm cube. So your volume needs to be in dm cube. You have to be careful to ensure that you convert your volumes to dm cube. I'm going to see if I can solve some questions on it, but these are the formulas you need on that. All right, I'm going to solve questions on that. Okay, we'll see if we could talk about that before the time ends. Can you draw the structure of any compounds? What am I
Yes,
supposed to draw? Okay, can you draw the structure of ionic compounds? What am I supposed to draw? Okay, structure of ionic compounds. First, you have to show how the ionic bond acts involve transfer of electrons, and then you have to know the meaning of ionic bonding. The right definition for ionic bonding is an electrostatic attraction between oppositely charged ions. So when you're drawing for ionic compounds, you just have to show how the metal loses electron and the charge of the metal. For example, if I want to form aluminium fluoride now, which is an ionic compound, right? All I need to do is to draw, you'll be given a space in your question paper to draw how the aluminium loses electrons. Okay, so for instance, aluminium has an electronic configuration of, aluminium has a proton number of 13, so it's 283. Fluorine has, okay, which is 27. So I'm going to draw this, okay. So 2 first, then I draw 1, 2, 3, 4, 5, 6, 7, 8. Okay, and then I draw the third one. So instead of drawing the third one, I'll just show how these 3 electrons are lost from here. Okay, so I'll simply erase this instead of drawing the third one. So you'll be given a space on your paper to write how many electrons do you think aluminum is going to give off. Then you draw that of fluorine, you'll be asked to draw 1 fluorine atom. So 1, 2, 3, 4, Right, so let me represent it with a different, since it's dot and cross. Right, so I'll represent it with a different diagram. So 1, 2, 1, 2, 3, 4, 5, 6, 7. So these are the 7 electrons outside. So it's going to receive 1 electron because there are 3 of them, but you have to draw just 1. So it's going to receive 1, and this is how I represent the 1 that was received from aluminium. So what it means is that aluminium gives out 3 electrons. This chloride ion receives just 1. Fluoride ion receives just 1, but there are several other ones, several other fluoride ions that receive it. So this is what you're expected to draw in most cases. Just draw one of the representation and show the charges. I think that's for ionic structures. Yes, concentration of acid doesn't increase the volume of gas produced. It only makes the reaction faster. All right, Adam, that's the answer to your question. It doesn't increase the volume of the gas. It only makes the reaction faster. Okay, so you have a steeper curve by increasing the concentration. Yes, somebody mentioned exothermic and endothermic. All right, it also has to do with the profile diagram. Okay, so the profile diagram. If the energy of the product is more than the energy of the reactant, it's going to be an endothermic reaction. But if the energy of the reactant is more than the energy of the product, it's going to give you an exothermic reaction. All right, so you should be able to draw a diagram representing the activation energy, the change in enthalpy, all right, and where the reactants and products are. You can check materials to review that. Amphoteric, acidic, and basic. All right, so amphoteric oxides, we have just 2 major examples, and we said they can behave like an acid and a base. So 2 examples of amphoteric are this and this. All right, these are amphoteric oxides. Basic oxides are simply metal oxides. So if we have a metal oxide, we simply call them basic. Then the acidic oxides are non-metal and oxygen. So we have a non-metal and oxygen. We call those ones the basic. So for example, carbon dioxide now is an acidic oxide. Okay, remember that carbon monoxide is a neutral oxide. All right. So this is an example. We can also have SiO2, SO2. So these are non-metals with oxygen. They form acidic metals and oxygen. And then these are the 2 examples of amphoteric. Oxidation occurs at the anode. Okay, not reduction for Fent's question. Okay, I think I don't think I'll be able to end this class if I keep on answering everybody's question. Okay, base, difference between a base and an alkali. A base is, okay, a proton acid. Okay, an alkali is a base that is soluble in water, right? So that's the difference between both of them. Okay, so what is going to happen is this bond energy. Okay, let me see if I could project a question that talks about bond energy, since we're having so many. Okay, I said I was going to solve something on stoichiometry. All right, let me solve something on stoichiometry, and I saw something on bond energy, and that will be the end of today's class. All right, I'm going to see, okay, there's stoichiometry here, but I'm seeing there's bond energy right here. There's no bond energy here. Okay, let me just solve stoichiometry, and then I'll check another paper to see bond energy. All right, so, and when I'm done with this, that'll be the end of today's class. I think I've done enough. All right, so let me solve stoichiometry. For the person that asks on stoichiometry, all right, so this is a question. It says manganese 4 oxide is added to 20 centimeter cube of aqueous hydrogen peroxide. The total volume of oxygen gas produced is this. Right, so now, the first question says, calculate the number of moles of oxygen gas. Now you're finding a gas. And I said the number of moles of a gas is the volume of the gas divided by 24 dm cubed. Okay, so that's what you need to look out for. Is it a gas? Is it a solid? Or is it a solution you are talking about? So this question is talking about the gas. So do we have the volume of the gas given in the question? Yes, we have the volume of the gas. Okay, We're told that the total volume produced is 72, but it is in cm cube. So if V is 72 cm cube, to convert it to dm cube, remember that 1000 cm cube is equivalent to 1 dm cube, right? So if we convert 72 cm cube to dm cube, okay, so we convert that, we're going to have 72 divided by 1000. So N is simply going to be whatever you obtain from this. I think that's going to be kind of 0.072 divided by 24. All right. So if you use your calculator on this, let me use my calculator over here so that I can be fast with it. Okay, so using the calculator, first is 72 divided. Okay, so this is 0.03. All right, now the next question says determine the number of moles of hydrogen peroxide which react. Now remember that we have gotten the number of moles of gas. Now we have to find the number of moles of this that reacted. Okay, so we could simply use stoichiometry, because if you look at what we only have the volume here, which is not enough to find the number of moles. So we can use the stoichiometry. So volume of 0.03, this is what we have obtained here, right? 0.03 moles for the gas. So applying stoichiometry using their ratios, right? So if we look at ratio, in terms of ratio, it is 2:2:1. Okay. So if 1 is 0.03, that means 2, this is double of this. Okay. This one is simply double of what we have here. So if we double that for hydrogen peroxide, we have 0.006. All right. And then the concentration of aqueous hydrogen peroxide in mole per dm cube. Now, this is a solution in mole per dm cube. And remember our formula for number of moles in mole per dm cube is C times V. But we have to find C. Okay, do we have the number of moles of hydrogen peroxide? Yes, we've calculated that here. Do we have the volume of hydrogen peroxide? Yes, it's given in the question to be 20. Okay, so we can solve now. So we'll have C to be N over V this time. So V is 20. So convert 20 to dm cube. So that's equivalent to 20 divided by 1000. Okay, so 20 divided by 1000, that's 0.02 dm cube. All right. And the number of moles is already here. So we can solve now to C equals to 0.006 divided by 0.02. So by the time you divide that, let me see what I have, 0.02. So I have 0.3. Okay. Now the next question is now saying calculate the concentration of aqueous hydrogen peroxide in gram per dm cube. Now we have the concentration in mole per dm cube. So to calculate this in gram per dm cube, it's simply going to be concentration in gram per dm cube is equal to, I didn't add this formula, so add it to your collection. Concentration in mole per dm cube times the molar mass of the solution that you're talking about, which is hydrogen peroxide. So we have the concentration in mole per dm cube, which is 0.3. We have to find the molar mass of hydrogen peroxide. It's H2O2. So it's going to be 1 times 2 plus 2 times 16. So that's 32 plus 2, that's 34. So it's going to be 0.3 times 34. All right. And if you do that multiplication, you have 10.2. So that's how to solve questions on stoichiometry. It's pretty easy once you know the formulas and what you're expected to look out for. All right. So I'm going to simply go to a question on bond energy. After that, we'll round the whole thing up. Let me see if I could see a question on bond energy. Okay, so I think this is a question that we can, attempt on bond energy. Okay, so for those asking for questions on bond energy, I think, yes, it will be posted soon. It will be posted soon. Yes, for the question on impure and pure silver. Okay, let me just briefly touch that. Pure and impure and pure silver. All right. So, when you're doing electrolysis, where you have to purify, application of electrolysis in purifying substances, okay? What you have to do is, the impure silver will be at the anode. So the impure parts, the impure compound you're trying to purify should be at the anode. Okay, so the impure one should be at the anode. And why it should be at the anode is because loss of electron occurs at the anode, right? While the pure part should be at the cathode. So what happens is that the impurities will remain at the anode while the pure portion leaves the anode to the cathode. So the essence of putting the impure one at the anode is because loss of electron always occurs at the anode. So when the losing of electrons occurs, the pure ones leave the anode and go to the cathode. You are now left with only the impurities at the anode. Okay, so that's the principle behind putting the impure part at the anode and putting the pure one at the cathode. All right. Okay, so let's briefly do bond energy. Okay, so the first question is you are given a lot of information and then you are asked to, calculate the energy needed to break the bonds in the reactant. Okay, so for us to get the energy needed to break the bonds in the reactant is to look at how we're going to break all of this. Okay, so you see that the breaking is going to occur, occur here, occur here, occur here, occur here. It's going to be breaking right here, and right here. So we are now left to calculate how many of them have been broken. So how many CCl bonds were broken? 4 of them. So 4 CCl bonds were broken in the reactant part. So 4 CCl bonds were broken, plus how many OH bonds were broken? 1, 2, 3, 4. 4 OH bonds were broken. All right. So 4 CCl bonds. So we have CCl here. So 4 times 340. So it becomes 4 times 340 plus 4 times how many OH bonds were broken? 460. So we add that up. So it becomes 4 times 340. Okay, which is 1360 plus 4 times 460, which is 1840. So if we add all of this up, so I have 1840 plus 1360. So we're having 3,200, kilojoules. So this is the reactant end. So that is what we do for the bond, the energy required to break the bonds. All we need to do is to just count how many all the bonds and impute the number times the energy required. All right. So the next one says calculate the energy released when the bonds in carbon dioxide form. So when the bonds in carbon dioxide form, this is carbon dioxide. So when the bonds in carbon dioxide form, there's going to be a break here, and there's going to be a break here. So we're breaking at 2 positions here. So CO, CO. So we have 805 for the carbon double bond O. So we're going to have 2 times 805. We'll just do 2 times 805. And that's going to give us 1610. Because we're doing 2 times 805 for this. All right. Calculate the HCl bond energy. So we're asked to find the bond energy here. And remember that how many HCls are needed to be formed? 1, 2, 3, 4. We need to form 4 HCl bonds. So we need to form 4 HCl bonds. And we are already given that the the energy of the reaction is minus 130. So we're going to use that to solve as well. So let's start with the energy of the reactant itself. Remember that to get the energy of the reaction, so the enthalpy, change the enthalpy of the whole reaction is simply the enthalpy of the reactant minus the enthalpy of our products. Okay, so the sum of the enthalpies of the reactant minus the sum of the enthalpies of the product. So the sum of the enthalpies of the reactant was what we did here. Okay, and we already know the change in enthalpy of the whole reaction. The change in enthalpy of the whole reaction is minus 130. So we just put that there. Minus 130 is equal to the sum of the enthalpies of the reactant was 3,200 minus, into brackets now, the sum of the enthalpies of the product. We are left with an unknown, which is this. So this is one product and this is the second product. So since we are left with an unknown, this is what we are looking for. And we have to sum them up. So we already have 1610 as the enthalpy of the first product. And for the second product is the unknown, which is HCl. Okay, so we're going to solve this mathematically. It becomes minus 130 equals to 3,200. So we open the brackets now, minus times 1610. Okay, Minus times plus is minus 4HCl. Okay, so we could move the unknown to the other side. It becomes 4 HCl equals to, on the right, 3,200 minus 1610. This moves to the right to become plus 130. All right. So from here, you could use your calculator, 3,200 minus 1610, okay, plus 130. So I'm having 1720 for HCl. Okay. Then I'm looking for HCl, so I can divide by 4. Right? So by the time I divide by 4, the bond energy of HCl is simply 430. So 430 kilojoule per mole. All right, so all we need to do is to just put 430 here. All right, so I believe I've solved, though there are certain points I've not made yet, but I just want to close by saying this summary. So for those that are just joining late, please listen to this summary on likely questions that you're going to find. And for other questions I've been able to treat, please pardon me at some other time, or you could simply use the bond breaking is the energy required to break bonds. While bond forming is the energy required to form products. So bond breaking is the energy required to break the bonds and the reactants. Bond forming is the energy required to form products. Okay, so let's listen to this. I know there are some questions I've not touched, but we could spend the whole day solving. All right, but it's all boils down to, yeah, there'll be no meeting tomorrow, please. But you can post whatever challenge you have, on the you can post whatever challenge you have on the page for chemistry, and I'm free, I'll just chip in answers to them. All right, so review. Let's look at questions you should expect. You can't escape questions on rate of reaction, 1. You can't escape questions on electrolysis, whether it is electroplating or you're asked to describe a process of electrolysis, what is deposited at the cathode or at the anode. So expect questions on electroplating, electrolysis of solutions, whether it is molten, concentrated aqueous, or dilute aqueous. Expect questions from there. You should also expect questions from reversible reactions, okay, and equilibrium. Expect questions from reversible and equilibrium reactions and how to interpret them. Expect questions on polymers and organic chemistry. Okay. Expect questions on reaction conditions for either the contact process, Haber process, hydrogenation, hydration, fermentation, esterification, or combustion. It could be any of the reactions. So expect some questions from that angle. All right. Expect some questions from what is activation energy? When you talk about chemical energetics, expect questions from activation energy, bond energy calculations like we just finished doing. Yes, and expect definitely compulsory questions from stoichiometry. You will definitely have questions on stoichiometry. You could be asked to find the water of crystallization. Okay, so expect questions from there. Expect some questions from salt preparation and acid base. Yes, you should know your indicators and their colors in different medium, such as methyl orange, thymophthalene, universal indicators. Okay, expect questions from your indicators and their colors in different mediums, like I said. Okay, so equally expect some questions from chemistry of the environment. All right, use of catalytic converters, flue gas desulfurization, greenhouse gases, okay, harmful substances and non-harmful substances. You expect little questions from there, right, to test your knowledge, and also questions from, some questions from paper 6, such as tests for some of the ions, tests for hydrogen gas, tests for oxygen gas, tests for carbonates, sulfur dioxide, or the sulfite ion. So expect some questions from flame tests. Sodium gives a yellow flame, right? Potassium gives a lilac flame, all right? And calcium gives an orange red. Again, test for saturated and unsaturated hydrocarbons, using aqueous bromine. So you have to know what happens. Remember, it polarizes the unsaturated one, it polarizes bromine water. So moves from orange to colorless. You have to know that. Now, when someone is asking conditions for combustion, what you simply need is air. Okay, air. So if it's excess supply of air, you have carbon dioxide and water. If it's limited supply of air, you have carbon monoxide and water. All right. So expect questions again from drawing energy profile diagrams. Okay, you should be able to draw energy profile diagrams, labeling the activation energy, the enthalpy, okay, of everything, extraction of iron and aluminium, read it thoroughly, and why you add cryolite, why you use coke, why you use calcium carbonate. Review all of this because you could have questions on them. All right, I already said you should be able to prepare insoluble salts, so expect questions from that angle. All right, test for water. Yes, test for water. Expect some questions from there. Expect some questions from I've talked about extraction of iron and aluminium. All right, so expect some questions from, yes, isotopes. All right, I to calculate isotopic abundance, relative atomic mass. Not as many questions on isotopes because you could have questions from that angle. All right, I think I've touched majorly the areas. Of course, I believe everyone should be able to solve protons, calculating the number of protons, electrons, and neutrons. That's quite easy. All right, so I don't think anyone should have a question. Then acids, how to dissociate acids. Okay, weak acids, remember what acids are and what bases are, what alkalis are soluble bases, right, and many others like that. So we can go on and on, and but the major thing is when you read enough, when you study enough, right, you'll be able to effectively answer any form of question.
Excuse me,
So
sir.
I'm going to hand over. Yeah, go ahead.
So
Yes, DB, go
do
ahead.
you think there's anything that's like not coming out?
Anything that's not coming out, I'm not sure about that. Okay, as long as it's in the syllabus, is either going to come out on paper 4 or paper 2 or paper 2. So everything needs to come out except those things that are not in the syllabus, right? So, but there are certain things that you cannot escape. All right, rate of reaction, electrolysis, organic chemistry. Okay, you can't escape questions from those angles. Stoichiometry, those ones are definitely coming out. All right, acid and base are definitely coming out. All right, any other question?
All right,
Mr. Ajiro.
AFS, ask your question. Yeah.
Yeah, I have a question. What do you think is the hardest question? Like on what topic will we ask them? Just a rough
Yeah,
estimate.
yeah. From the examiner's report, most people could not explain equilibrium properly. So take note of this. And I told you in this class that if you are explaining equilibrium, 2 things are important. Rate of forward reaction is equal to the rate of backward, and the concentration of reactants and products are constant. Most students wrote the concentration of reactants and products are the same. No, they are not the same. So these are some of the difficult questions. Now, the other question that most students found difficult was explaining how greenhouse gases causes global warming. Yes, this is one area in the examiner's report that students failed woefully. And this question was, yeah, I'm going to teach you how to answer this. This was for 3 marks. Okay, explain how greenhouse gases causes global warming. So first thing is, for the first mark, talk about the fact that the sun emits thermal energy to the earth. So sun emits thermal energy to the earth. That's mark 1. The second mark is the earth reflects the thermal energy. The earth reflects the thermal energy. All right. And then the third mark is that greenhouse gases absorb this reflected thermal energy. So greenhouse gases absorb the thermal energy and result in global warming. So this is how to get the 3 marks. The greenhouse gases absorb the thermal energy, which results in global warming. So this is where students, didn't do well. The question is, how does the greenhouse gas cause global warming? Explain how greenhouse gases causes global warming.